Advanced Gaussian process research across 3 different fields for decades. So hopefully, let's look on the upside. And it's a great pleasure to introduce Hans Wackernagel, who we've mentioned several times already in presentation, who's going to tell us about geostatistics for space-time analysis.
Yes, thank you very much, Neil. I'm going to talk about geostatistics, but also about data assimilation. So I'm going to move rather swiftly from Kriging to Ensemble Kalman filtering at some stage. And I'm working since quite some time with Laurent Bertino on these topics. Space-time geostatistics, in the way I'm going to present it today in a rather introductory talk because of the very mixed audience we have here, will depend on a central question. Is a physical numerical model implementing partial differential equations available to describe the time evolution of the system, because the time dynamics are often highly nonlinear, and statistical methods alone, using only data, actually give quite poor prediction because the behavior of the phenomenon is very hard to predict if you don't know the nonlinear interactions between the variables, which are described generally by such a numerical model. Just to give an example to which I will come back. So if you have under our climate in winter, the plant system is not there's no growth happening of the plants, and then at some critical temperatures suddenly you have this spring bloom, and this is the example of a highly nonlinear event, very difficult to predict, and you should put some knowledge into some model which can be deterministic or stochastic to describe this time evolution and this sudden change in time. Yeah, but not in all situations you have that. So I will begin with the case you don't have it, and so you will be very interested in setting up covariance functions, space-time covariance functions, sometimes even multivariate, as Peter this morning started talking about. And then I will quickly, this you do in order to do some Kriging, which was has been often mentioned in this workshop already. And actually, I thought a moment I would speak about geostatistical simulation, but I won't, because of lack of time. And then I will go over to Ensemble Kalman filtering, which will actually make use of a physical model. So just to begin with, a little warm-up example, very simple and very classical. So it's from the book of Box and Jenkins, very famous, about time series analysis, and the data set is easy to find on the web. And so it describes there's a gas furnace, and you have some gas entering, and there's a chemical reaction, and then a bit later there's a modification of the CO2 output as a consequence of this. And so if you have 2 time series measured at the same moment, and you look at them, so the first thing you might do is just do a scatter plot, very basic scatter plot, and what you see is that gas and CO2 are negatively correlated, not very strongly, and there's a lot of scatter, but there's still some tendency to be seen. Now we look at the time series. Always good to look and healthy to look at the data, and so if you look at the gas, it goes down, and then the CO2 tends to go up at, for example, here it's low gas, higher CO2 and so on. So you see there is some anti-correlation visible. Now what is interesting is to use some cross covariance function. So if I is the gas and J is the CO2, so you will retrieve the mean in one formulation of the classical formulation of the cross covariance function, and then multiply. I put a cross here to say it's cross correlation, but simply multiply with the residual of the CO2 with respect to its mean. And if you do this on this famous data set, you see that you have a covariance function which reflects the negative correlation, and it's the maximum negative correlation is not at the origin but shifted by 45 seconds, which is the time it takes the chemical reaction to take place. So very often you don't know exactly the physical process, and it's always very interesting to compute these types of covariance functions. So the cross covariance function obviously is not an even function, it's not an odd function either. It's something quite general, and you can easily have in space-time data such sort of delay effects, sometimes quite complicated. In time there's only one dimension, so you might identify them easily, but in space the shifts could be in various directions in the field, and so they are very difficult to understand and to model. Yeah. So this just was to show you that you have some very general types of functions. And so here are some classical properties that were alluded to this morning by Peter already. So he has shown some example of separable space-time covariance function. So Z is the quantity we're interested in, our data. X is the spatial coordinates in d dimensions, 1, 2, or 3, and R is and T is the time coordinate. And so you have, if you compare the data at two different locations in space and time, different in space and different at a different moment in time, then if it might, in general, this covariance has is very complex, as like the cross covariance function. But it may happen, and it will be interesting for applications to check whether you have some separability. The phenomenon is actually has a quite simple space-time structure, and then if you have this separability, many simplifications occur in the processing. That's why it's interesting and in the modeling. So it's why it's interesting to check whether on data whether this is actually the case. Now you might also have the property of full symmetry. So if you exchange T1 and T2 as is done here, this doesn't affect the value of the covariance function. And finally, it's also interesting to know whether the covariance is translation invariant. So this is called stationarity. And so there's a nice plot in a paper by Gniting, Janton, and Coutorp that shows how these different assumptions are imbricated. So space-time covariance function a priori is something quite general, but in your application maybe it might be appropriate to assume stationarity, and then to check for full symmetry or even for separability. Yeah. And so I want to show examples, because Peter has done already, thank you Peter, this morning, of space-time covariance functions, and I will just briefly mention from that paper a case study which you might look up. It is very nicely made, and it's a very famous data set from a paper by Hazlett and Raftery, and it's about Irish winds, and you easily find it on the web in several places. And so the winds are predominantly westerly, and so the velocities propagate from the west to the east, and so actually the temporal correlations have a lead or lag between east and west at a daily scale, so it's really at a quite large temporal scale. And in the paper they have done exploratory data analysis. Various authors, they were not the first one to analyze it, and it shows that there's no such thing as full symmetry or separability that can be assumed for the data. Nevertheless, they make the experiment to fit 3 different models, one separable, the other fully symmetric yet not separable, which is a bit more general, and then a merely stationary model, but which is not even fully symmetric. And the numerical comparisons show that actually the simplifications or the simple models do not perform well, as they do not correspond to the physical reality. So you can see how important it is to check whether this or that assumptions fits with your data. Now you might separate the covariance, but you might also study a separable mean field. And so, for example, in Séguret and Huchon, in a paper of 1990, they have a trigonometric signal with several components. And I'm going to quickly present this case study to make the talk more lively. In fact, it's about Earth magnetism. Magnetic anomalies are interesting to study Earth history, and they are influenced by several external factors. Maybe I could use rather this screen, as I have a pointer. You have the solar wind, which explains daily fluctuations, the rotation of the moon, which is the well-known cycle of 28 days, and finally a half-year cycle of solar perturbations. And the data that was looked at in this paper stems from an oceanographic campaign, a research vessel, which measured magnetism over a rather large area of 111 square kilometers of Peru. And the fluctuations of magnetism are actually available at an observatory at the coast nearby. And so here you have, over 6 days, the fluctuations of the Earth's magnetism at that observation station. And you see how complicated these fluctuations are, because there's an overlay of different cycles at different frequencies. And if you compute a variogram, which is a rather similar thing than the covariance function, yet a bit more general, you see clearly the periodicities appear. The campaign it stems from, so this is Peru, and here is the area that where this data stems from, so this is the zoom of that area. And So you see the ship, it took it 6 days to do this campaign to sample the data. And as you have seen from the previous slide and understood, there's a lot of perturbation happening on the measurements that are due to the fact that the data, these spatial data, were taken at different times. And so you have here the perturbations from the observatory, and down here the measurements by the boat. And as it always happens, at some time the measurements couldn't be done and were delayed by several hours. And so actually using Kriging to filter out the time perturbations, if you neglect these time perturbations, you get this map, but actually it's quite wrong because the data is so perturbed, and you might easily, by linear filtering through Kriging, remove the perturbation and get then the real picture invariant in time of the magnetism. So it's just a simple example. So Kriging, so you may filter mean. Let's come back to filtering covariance. So the usual simple Kriging that you have studied in this course and seen several times, and you have seen this type of equation. So here I simply separate CO, which is the noise, some noise, C0, and white or red, and the actual covariance of the phenomenon. And so this is the usual equation we have seen. And now if you want to do filtering, so instead of computing a surface that passes through data point, doing exact interpolation, you might simply remove in what is the right-hand side of the Kriging system. So in the numerator, you might remove the error while it is still in the denominator. And so this is the Kriging system. I don't give you the details how to set it up in this way, but it's a very simple linear model. And
let's check with the error observation. That's also in this case a function of x. It's not an independent error.
The error, in fact, is identified on the covariance function or variogram. In our case, it's the nugget effect typically that you want to filter out, or even a small scale variation to show only the large scale variations. Yeah, and so this matrix here, this product of the right-hand Kriging vector and the left-hand covariance matrix, its inverse, we might call the Krige gain. And you see that it has the structure, and here there's this hole because we have removed the noise covariance. And to filter the data and obtain the underlying variable unperturbed. And now, why do I say Krige gain? Because this is not Kriging weights as one would usually. It's to refer to Kalman filtering. And so here's the well-known linear Kalman filter. This prepares also for the next talk. So you have two steps in the Kalman filter: the propagation step, where you have all the forward equations, and so where we move from time t to t+1 using some linear model, and we also keep track of the covariances, the model error. And in the same way, then the second step is the update, and where we then use the new data that has arrived at t+1 and integrate it into the filter at this stage. So And so I won't give too much detail on the Kalman filter. What I want to mention is that you have here this very famous Kalman gain. And the Kalman gain, actually this equation, update equation, is a simple Kriging, or because simple Kriging is a multiple linear regression. And so you have here a Kriging, and it is really a filter because you have here the error covariance, which is not present. Yeah, and so if you have the chance to have a model describing, numerical model describing the nonlinear dynamics in time, because this is generally what is the case in geophysical systems, you might then be interested in the Ensemble Kalman filter, which is very much used nowadays in oceanography, also meteorology more and more, and in oil reservoir optimization at a more experimental stage right now. But since 10 years there's growing interest in that, and there are some fields by Statoil where it's applied by Geir Evensen, by the way, who is the creator of that Ensemble Kalman filter. And so the idea is very simple. So you have the model. The model is just a black box. You don't need to put your fingers very deep inside. You just need to access to the state vector, and so you perturb the initial and boundary conditions of the model. So these are the perturbations U, and you obtain a number of predictions, and this ensemble of predictions or forecasts, which are denoted by F. This ensemble does not need to be very large. So the thing is applicable to very large systems. So typically N will be 100 or 400 nowadays with the present computing means. And the whole thing is also easily parallelizable. So you can run all of the model in parallel on many processors, all the processors you have available. And then the update step also is done separately on each trajectory of each ensemble member. And in the initial paper by Evensen, you didn't have this perturbation of the data, which then was introduced in 1998 because it's really necessary for the filter to have better properties. And H, by the way, is the observation operator, which may be nonlinear also. And so this is the 1998 version of the filter. I think for this public, this is enough. And there are many different variants that have been proposed since. So I won't go into a detailed discussion. So, but just to show you the basic idea, which is really very simple to implement. And so the covariances matrices of the forecasts and the observation errors. So the covariance matrices are gained simply on the ensemble and are derived from the ensemble of forecasts, as well as the update covariances, which resemble to, or which are the equivalent of the Kriging errors variants, are computed directly on the ensemble. So it's really very simple to get the parameters. And so what is actually the Ensemble Kalman filter? It is a clean generalization of the linear filter, because with an infinite ensemble in the Gaussian case, you will have as a limit the same result as the linear Kalman filter. So you come back to that result. The Ensemble Kalman filter is actually not simply pure resampling of a Gaussian posterior. It's only the updates that are linear. So the data to which you apply it may not be non-Gaussian. And then in the update, they're added to the prior of a non-Gaussian ensemble. So the updated ensemble will hopefully, and seems to inherit many of the properties of the non-Gaussian ensemble. And in summary, so it is computationally efficient because you don't need a big ensemble of particles in this framework. It is a rather modest ensemble compared to the size of the problems it is applied, and the solution can be seen. It's as somewhere in between, midway between the linear update and the full Bayesian computation, which would be the ideal. Yeah.
I think I've never understood about the Ensemble Kalman filtering.
Yeah.
Why you perturb the data? He said Evanson had it in his original proposal, and it feels like the wrong thing to do to move your data. I mean, why does that make it work better? So if you added due north and the...
Yeah, it was, you need to enrich the data. I mean, this without this perturbation, the filter would not converge well. So this was...
Just a hack that found...
but which is necessary. Yeah.
Is there an equivalent of that in a full particle filter?
It's not at all a particle filter.
It's not a particle filter, but in particle filters you do something similar, I think.
You don't perturb the data.
But it's like...
Is it like sample replenishment?
Yeah.
It does it. People do horrible things to the likelihood they will tell you about in particle filters, which is why so if they call it sequential Monte Carlo, I assume they're not doing horrible things to the likelihood. But when they call it particle filters, I assume they're prepared to do horrible, incorrect things to the likelihood, which are equivalent. They anneal the likelihood, right? That comes to the same thing, to sort of scale the log likelihood down to ensure that particles that would have been knocked out are upweighted. They do that across large areas in bootstrap particle filtering, but they don't write about it. And at least these guys are being honest enough to say they have to do. I think it's kind of equivalent. Is that?
Yeah. So in particle filtering, you often end up with a sort of degenerate posterior. You do some resampling, and you find there's many of your particles are really low weighted. I imagine that, and then one of the hacks is to do exactly this: is to sort of spread the particles out a little bit.
But you need to recall that you're approximating the Kalman filter right now. So your optimal is the Kalman filter already. So particle filters try to go beyond that already at the start. We are just chasing behind Kalman filter now. So that's an approximate Kalman filter.
That's a what?
So you in low dimensions you can actually implement the actual Kalman filter.
Yeah.
And that will just solve the linear problem.
Yeah.
But particle filters are about non-linear problems.
Yeah.
So it's like a different regime of problems.
I don't see this like as resampling at all, but I don't understand.
No, but they don't. What I'm saying is, you do likelihood resampling because you call it sequential Monte Carlo, so you care about its correctness. When people implement it for visual tracking and they don't really care about the posterior, they're just looking for an algorithm. They very often, or they don't write about it in their papers, but you ask the students that implement it, they very often have changes to the likelihood that avoid them having to do particle resampling in order to prevent that happening. And that's why I don't like particle filters, but I do like sequential Monte Carlo, even though they're the same thing.
But with particle filters, you cannot have a very large state vector. Actually, it needs to be quite small, about 10 or so, although the experts say you might, Okay, then you have, again, many different brands, flavors, rather. Okay. So just a very small toy example. First, Ecological, as there are many biologists in the room, or some at least, but I am not a biologist, so please forgive my my poor presentation of it, but so it's a very simplified ecological model with nutrients. So this is a water column, and that's time over 1 year. And so this model, simplified model, simulates the evolution of the nutrients in this water column over the year. And you see that suddenly in spring the nutrients lower a lot. They lower. They go from dark blue to light blue, because in spring the phytoplankton suddenly, there's a spring bloom, and the phytoplankton becomes active and feeds the nutrients, and then the phytoplankton itself is consumed by the herbivores a bit later. So you have first an explosion of the phytoplankton, and then a bit later of the herbivores. And to apply on this toy example the Ensemble Kalman filter, the data samples were taken, some data was generated from the model by sampling it every 10 days and perturbing it actually by different noises. Here I only used the white noise example. It was also done by colored noise in other versions of other ones. And the ensemble is just 100 members, as it's quite standard. And now we want to just look at what happens with the filter if you have, if the data is not Gaussian, or if it is closer to Gaussian after a logarithmic transformation. So here the first row is the original data. So from this model you have the nutrients, the herbivores, the phytoplankton, and we are in fact interested in predicting the two latter ones. And you see that the herbivores and the phytoplankton are very skewed on the right. The distribution is very skewed on the right, so very different from the realization of a normal distribution. And if you take the log, in fact these two variables come much closer to what could be the distribution is much more symmetrical. And we are not too much bothered that the nutrients are now skewed to the left instead of the right. And so if we apply the Ensemble Kalman filter on that, we see that the spring bloom of the phytoplankton and the herbivores, so in the left column with the regular Ensemble Kalman filter applied with raw data, there are a lot of false starts of the model, and the spring bloom is wrongly predicted. The scale here is black if it is very far from zero, both positive or negative. And so if you bring your data closer to the Gaussian assumptions, actually the prediction works much better, the forecast works much better, and so you see that there is still some sensitivity to the Gaussian hypothesis. Now these type of algorithms are applied since now more than a decade to very large oceanographic systems, and you have here the sea surface temperature for the whole Atlantic. You see South America, the Gulf of Mexico, and the Gulf Stream that goes north towards the coast of Ireland and England. And that's why it's warmer on the west coast than on the east coast, warmer in Glasgow than in Aberdeen in winter. And well, that's not what my talk is about. And here on the right you have the forecast variance, CF. and that is so at the propagation step. And now if you go over to the update, you see that there is much more detail. I go switch between the two, you see, so not too fast. You see that after the update you have much more detail in the map, and by integrating satellite data and a lot of mainly satellite data in that example, but also you may integrate oceanography data, but a great many. So it's really a very big data set and a huge state vector, and also the variance has been reduced substantially through the update, through the new data, thanks to the new data that has been incorporated in the filtering. Yeah, so I'm quite reasonably in time, and so let me first make a quick summary. So as I mentioned, the idea of this talk was to say, if you attack space-time phenomena, always check whether you don't have a physical model available. It might be of help. In epidemiology, actually, we applied such data assimilation, but using a particle filter, by the way, with a stochastic SIR model, susceptible, infected, recovered. And there we had a quite small state space, so particle filtering was a very good idea. It's a much better idea than Kalman filtering, because you don't have this Gaussian assumption, as was mentioned already in the room. And so first case, if you don't have this model available, you might be interested in fitting some space-time covariance and go for some type of kriging or estimation, or if you have count data, like the one Peter mentioned, the approaches Peter mentioned this morning with Cox models, and the space-time structure, it's of advantage to check whether simplification is realistic, and then it will simplify the approach a lot if this is the case. And otherwise, state space models are give a framework for various flavors of Kalman filters, and in the next talk there will be a few other variants presented, but Simo will do that soon. So, but before we go over to the next talk, I still put here, because there were many questions about geostatistics, what is it, and so on, in the room these last days, and I had some echoes through Neil in particular of that. So I put not only references which refer directly to the talk. So the first thing I want to say, so like Peter mentioned this morning, really the most complete reference book on geostatistics is now the Chiles and Delphinaire second edition, and the talk you have just heard is built up exactly inspired by the structure of his nice chapter on space-time models in the book. And so after evaluating literature, I found that it was a very up-to-date summary of space-time geostatistics, but not about the models that Peter presented this morning too much, because they are applied in epidemiology, and so it's rather on continuous variables. And now on data assimilation, that's the one standard work. Yeah, what I didn't mention geostatistical simulation, but you must understand that kriging is not the main thing in geostatistics nowadays. It's rather simulation. Industry, the questions asked by industry are generally solved by some methods using some Monte Carlo methods, and not linear approach, like estimating the probability of exceedance of some variable. using estimators which are non-linearly related to the data. You can also do some analytical models, but for very particular simulations, situations, sorry. And simulation is a much more general approach. Yeah, and so finally there was some talk about the origins of geostatistics, but Peter mentioned it already this morning. So the first pioneering work was done in the 1950s, the thesis by Kriege in 1950, and then the young Materon at the age of 25 wrote his first paper in Annales des Mines on that subject, and then wrote several books, the two major books in the 1960s. But also he worked on random sets very early, and there's another community, very different, more close to stochastic geometry, that then is interested in the random sets theory, for which Materon wrote really the very basic text. And these random sets are especially interesting for simulating spatial phenomena, and so this is also very important in spatial simulation. And finally, Materon also wrote a philosophical text about geostatistics, which just has been republished by the École des Mines, because Springer didn't reprint it. Yeah, and you find in our electronic library all the writings of Materon, because he left a great many notes and short reports with interesting ideas. But their first difficulty, they are in French generally, and the second difficulty is that the ideas are really, it's not easy to read. But it's this treasure that where many ideas can still be exploited. I just wanted to mention it. And last, there's software around. So here clearly I have a bias towards Fontainebleau, because we have also now a package in R, which is much used by statisticians like Peter, but not so much by machine learning people yet. They often use more MATLAB, but you can use it in a MATLAB-like, have the MATLAB-like feeling if you also download this here. We had just a discussion at table, that's why I include this. And so I also want to mention that you can use RGOs for response surfaces, because it's not limited to 3 spatial coordinates, but n whatsoever large. And there's also a commercial software much used by industry. And finally, for Ensemble Kalman filtering, you have a MATLAB package on this page here. Yeah, thank you, Neil in particular, and the group for inviting me to talk here at this workshops. And finally, well, just a new project mentioned that will start next month, which will allow us to continue with Laurent Bertineau to work on these subjects. Okay, that's all. Thank you very much. That's Swiss precision, isn't it?
Swiss precision, yeah. And it's great. We've got a temporal-spatial constraint, which is there's coffee in the common room now. But I think there's time for questions for Hans.
Yeah, sure.
I really enjoyed that. I really like the graphical tools you had at the start for looking at the covariance. So if you wanted to detect a non-separability, what should you look at to easily detect?
In fact, one in multivariate setting. In fact, I have not done that much, not as much as Peter space-time geostatistics, but in the multivariate, for that function, multivariate function, there's a very common formula used in time series analysis, where in fact general covariance can be split into an even and an odd term, and you can also compute the two empirically. and if the odd term is almost flat, then you have an even function, and so it's then symmetric. Yeah. And well, in the multivariate case, there are some tests around using PCA, for example. There are several ways to test, but it maybe would take me too long to give you this topic.
The cross-correlation plots, you're getting it from a test function, essentially.
Maybe you have several ways to approach it. I mean, for separability in the multivariate case, to know whether the data are intrinsically correlated or not, I have at least 3 ways of approaching it. And then you have also, yeah, for separability there was Boli and Janton who have published a paper using a statistical testing approach.
Yeah, I mean, my own view is that there's a lot to be said for doing a non-parametric, smooth non-parametric estimate and then comparing it with the best fitting separable approximation and looking at the discrepancies, and if they've got a structure to them that makes sense and is capable of being modelled, then you do it that way. So I think of it as a kind of an informal model building process rather than necessarily requiring a formal test. But there is literature, as Hans has mentioned, about formal tests for separability.
Yeah.
Any questions? Great. So if we have coffee now, and we need to be back here. Is Alan around? Yeah. Are we all right? Coffee from till 3:30, and then we've got an hour. We'll run till 4:30 with Seamus talking.
So we could skip the last coffee session on this.
Huh?
We could skip the last coffee session before the discussion, or
well,
we will miss that.
I think we're going to end up missing the final tea thing. The thing, the tea at the end. Yeah. So cancel that, and what we'll go for. We'll have coffee now till 5:30. Timo will go from 3:30 till 4:30, and then we've got 15 minutes. Well, I mean, Timo leads the conversation. Timo, of course, has been the most mentioned speaker and the last speaker. Every other speaker has said, and of course, Timo will talk about that.
Because I'm the last.
So Timo's like the residual speaker. Everything associated with Gaussian processes that haven't been mentioned for the last 4 days will be covered in Timo's talk. Okay, so back to half.
So maybe you want to switch it on.